Yo, it's your boy Canfield. Hi everyone, it's Mr. Canfield. Today, we're going to be transcending algebra with the derivatives of transcendental functions. So something for us to understand is that in algebra, we have things like x squared, square root of x, x to different powers, these things called polynomials. We do algebra with them and stuff works. There are solutions to algebraic functions and algebraic things, and those solutions never involve transcendental functions. And so you have things like the natural log of x, you have things like e to the x, and these do not have algebraic ways to approach them. And so that's where we learned log rules and exponential things and did lots of stuff like that. And trig is also included in there. So we've already done some derivatives of trig. So, like pop quiz, what's the derivative of cotangent? Do you know it? Do you know it? Do you know that it's negative cosecant squared? Or do you forget? Anyway, here we go. So our first big deal, I don't teach all of these. The one that I teach is that the derivative of the natural log of x is 1 over x. So the natural log of x, when we take its derivative, we get 1 over x. If we were to kind of think about that in a different context, let's see if our first one says take the derivative of the natural log of 4x. So if I use my understanding of chain rule, this just says, oh, well, the most outside thing we have is natural log. So I'll do 1 over the insides. And then at the end of the day, it's important for us to remember that, well, I'm still need to do chain rule, so I have to multiply this by the derivative of the inside, which is 4, so times 4. And this is not a helpful way to write this. A more helpful way to write this would be 4 over 4x. And here the 4 is 4 divided by 4, they'll cancel. We wind up getting 1 over x. And this result is actually kind of interesting if we think about it, because the derivative of natural log of x is 1 over x. The derivative of natural log of 4x is 1 over x. What? They have the same derivative. And then if we were to go even further and be like, okay, well, what about the derivative of 12x? Like the same thing's going to happen. No matter what that number is, it's going to be 1 over x. If I were you, I probably wouldn't trust myself to go, oh, I know this every time, because we're not going to do lots of really simple ones like this. But it is an interesting result, and there's some reasons why this happens. So let's talk real quick. We're just going to do a quick aside. We're going to say, hey, natural log of x versus natural log of 4x. Why do these two have the same derivative beyond derivative rules? Well, so the derivative of this is 1 over x. That's fine. So here, but what if we say, I was looking into my camera when I wrote that. That's why it's so funky looking. All right. Let's look at this. So if this is f, then I could rewrite f using log rules. This says ln of 4x. Well, remember that multiplication inside a log turns into the sum of two separate logs. So now that we have the ln of 4 plus the ln of x, which is, it's the same thing as that. So if I were to take the derivative of this, well, ln 4, the natural log of 4 is a number. The derivative of a number is 0. The derivative of natural log of x is 1 over x. Oh, hey, look at that. So that's why that happens. So no matter what constant that is, that constant doesn't affect the rate of change. It's just a little interesting aside, not anything that you're going to need deep knowledge of. So now we get to something like this. It says the natural log of x squared minus 3. Oh, no. Go back. This is the other thing I wanted to talk about. The heck does ln x actually mean? So let's just talk about this for a minute. So I want to remind you that if we have 3 to the 4th power, that's equal to 81. And because 3 times 3 times 3 times 3 is equal to 81. So I'm going to use this to eventually get to ln. So I just want to remind you that 3 to the 4th is 81. I could have picked any exponential example. This is just what I decided to pick. So I can rewrite any exponent as a logarithm. And the way that that works is that's the base of my exponent. It's also the base of my logarithm. And we say, we know 3 to the 4th is 81. A logarithm instead begs the question, 3 to some power gets me 81. And so the logarithm base 3 of 81 is the exponent it would take to turn 3 into 81, which is 4. So the the shorthand of this is that the 3 stayed where it was, it just turned little, and then the 4 and the 81 switched places. So stay and swap. So, and this works for any sort of exponential situation. But then we run into, let's say we have e to the 3 is equal to, it's going to be some decimal. Okay, e to the 3 is some gross decimal because e is 2.718 and continuing forever. E is what we call a transcendental number. If you remember earlier when I was saying like E doesn't wind up showing up in algebra naturally. So E is never going to be an answer to a polynomial question. It's kind of outside of things that we solve algebraically. But then we lump all the log stuff in with it, but that's initially where it came from. So I can rewrite this as log base e of whatever the heck that is. I don't know what number that is. I don't care what number it is, honestly. Is equal to 3. And because the exponent and that switch places. So we developed a shorthand, we as in like people like a long time ago. They were like, you know what, we're using log base e so frequently, let's just call it the natural log. And so log base e turns into ln. It gets its own button. And so just to kind of belabor this point for a second, it's not like that because like people in the math education world want to make you suffer. It's not like that because the AP exam is like, ooh, let's pick this like annoying number that everybody hates. And no, natural log came out purely because of practicality. This number, this strange transcendental number that doesn't fit in with algebra, winds up being an excellent explainer for all sorts of things in nature, and in finances, and in all sorts of things, and in the way that things move. It's all over the place. And so they used it so much that they developed a shorthand for it. So just remember that this has a reason for existing, even if you don't see the reason today. So now, if we're on this next example, so like we just need to get the basics down, the basics of the mechanics of it, in order for us to move into, eventually maybe seeing some value in these problems. Okay, so y is equal to ln x squared minus 3. So then y prime is just going to be 1 over that. So instead of me writing like I did last time, 1 over 4x times 4, and then like I was like, oh, I'll just put the 4 on top, I'm going to jump straight to that. I'm going to put the x squared minus 3 on the bottom, and then instead of putting 1 here and times the derivative of that, what's the derivative of that? 2x. Let's just put it on top. There. Dunzo. So instead of having to kind of go through and do that, now I'm going to check for cancellations. Some people are going to try to tell me that x and x squared cancel each other out, and I just want to remind you. So like, let's say we have 2 over 4. We can agree that simplifies to 1/2, I'm sure. So so I'm going to have to stop using fun pen soon because I'm running out of ink. In comes boring marker. Oh, nope, that's dying. Now entering continually boring marker. Let's see. That shows up. Okay. So 2 over 4 plus 1. Let's look at what we know this is through PEMDAS. We know this is 2 over 5, which is 0.4. Is this the same as 2 over 4 plus 1? Can I simplify this and get 1/3? That's 0.3 repeating. So no, this plus sign jacks up any cancellations that we used to be able to do. So you really can't do things when there's pluses and minuses, separating our terms. So onward and upward. I don't know why I'm using lined paper. I much prefer blank paper. All right, so especially when I'm using markers like these. Okay, so 3 says y is equal to ln 3x squared minus 5x plus 8. So if I'm going to take this derivative, we'll put the 1 over that stuff, put the derivative of this on the top. So 6x minus 5. So hard. Number 4, y equals ln square root of x. I don't know why I wrote the problem. So I need to be careful. When I take the derivative, square root of x is on the bottom, and on the top, remember that square root of x is x to the 1/2. So the derivative of this, the 1/2 comes out front, there's an x inside, it goes to the negative 1/2 power. So I can rewrite this as 1 over 2 root x. Remember, because it's 1 over 2x to the 1/2. So then it turns into that. So the numerator of this is 1 over 2 root x. And this is illegal. This is an illegal form for us to leave an answer in. Fractions on fractions is not okay. So I'm going to talk about this 2 ways. I'll talk about the super slow way first. So this is saying 1 over 2 root x divided by the square root of x. And remember that currently the square root of x is over 1. So that's 1 over 2 root x times 1 over root x, because dividing by fractions is easy as pi. Just flip the second and multiply. So now I wind up getting 1 over 2 square root of x square root of x. Remember, 2 square roots multiplied together, well, that's the square root of x squared, and they cancel, and we just get x. So the derivative of natural log of square root of x is 1 over 2x, after all that. I want to talk about a different way to think about this. Personally, what I actually do with these is when I have a fraction on top, and there's no pluses or minuses, because remember, pluses and minuses ruin everything. But this is in the denominator of the top, so it just drops down here, and it's 1 over root x times 2 root x. Like, that's the way I would actually think about it. But this is why it happens, and if this isn't working, don't do this. Do this, it'll work. Remember, tricks only work if you get why they work, or if you're able to apply them correctly. All right. So in this next one, it says y is equal to x squared ln x. So it's number 5. That's it for what natural log is. It's just applying the rule in new situations. So like here, okay, well, I have 2 things multiplied together. I've got an x squared times an ln x. So I've got to do product rule. I'll take the derivative of the first one, and then I'll take the derivative of the second one, and leave stuff alone. That's it. You can literally be done here. I'm going to clean it up, but you could literally just leave it like that. So 2x ln x plus, now this is x squared over 1 times 1 over x, so that's going to be plus x. This is x times x over x, and one of the x's cancel. So you could write it like that. Woo. Let's look at 6. Oh, you just do quotient rule, right? ln x over x. So you just say, oh, okay. Well, the derivative of the top is 1 over x times the bottom minus derivative of the bottom, which is 1 times the top, all divided by the bottom squared. And I'm like, oh no, fractions inside fractions, but there's 1 over x times x, so they're going to cancel, and it's just going to be 1. So 1 minus natural log of x over x squared. Yay! Then we get to number 7. Gee, number 7 and number 6 look so similar. So this time, derivative of the top is 1 times the bottom minus derivative of the bottom times the top, all over the bottom squared. Now, ln squared, the way that we write that, don't do that. Because this implies we're taking the natural log of x squared. I would really recommend putting that in parentheses and putting a squared after it. It's very ambiguous otherwise and very dangerous. Part of me wants to write like ln squared of x, but that's not a notation that people use. So can't use it. Okay, so, oh hey, it like turns out to be almost the exact same thing as last time. ln x minus 1 over ln x quantity squared. Woo. So this is making me want to suggest something to you. Is this saying the absolute value of a dot nx squared? Is this saying 1 times 1x 1 times 1 nx squared? Is it saying L times ln x squared? I mean, I don't know why I was saying the squareds. Hopefully you see what I'm saying. Like, is this an L or a 1 or a 1 and an L or a 1 and a 1 and an L and an L? Like, what's going on? So I picked up a different way to do this, especially as a teacher, because I have to, part of being a teacher is trying to be as clear as possible for your students. So instead of writing ln like that, I use cursive. And I write a cursive ln, and that way I don't confuse myself and I don't confuse my students. ln also sometimes looks like absolute value, and it just gets really messy. So using a cursive ln can help. So if I'm trying to find the derivative of this one, this was number 8. First thing we'll do, well, we see it's something to the 5th power. That's the most outside thing. So that means it's going to be 5 something to the 4. What happens to the inside? Right, you leave it alone. And then we just have to take that times the derivative of the inside. Well, the derivative of ln is just 1 over x. I'm done. So we could clean it up if we want. We could say this is 5 ln x to the 4th over x, or a variety of other ways we could rewrite it, but that's it. So, okay, 9 through 12 are worth doing. They're worth talking about. When do we get to the fun one? Okay. Man, I'm gonna have to push you guys in class today. All right, so 9. So y equals square root of ln x. Well, so that means square root's the most outside thing. So that's going to be 1/2 to the negative 1/2 ln x, then multiply by the derivative of the inside, which is 1 over x. So we should clean this up. So we got 1 over 2x, right? And then square root of ln x. So this is getting flipped. Those are already on the bottom, so this joins them on the bottom. 10. Y equals cosine of ln x. So don't freak out. It's not that big of a deal. Y prime is going to be, well, what's the most outside thing we have? Cosine. So then what's the derivative of cosine? Negative sine. What do I do to the inside? Nothing, leave it alone. ln x. And then make sure you multiply by the derivative of the inside. Do the chain rule. That's it. It's gross. Like, I'm not like, hey, this is super nice looking and I'm happy about it. No, but the mechanics of it are easy. You go, okay, most outside thing, do that. Focus there. We're done. Now focus on the inside. You know, it didn't change inside, but its derivative popped out. So then we get to 11. 11 says y is equal to ln cosine x. Literally the same idea. Okay, y prime is equal to, oh, I need to first take the derivative of the outside thing, which is ln. The derivative, that's 1 over the inside, which is just cosine. Oh yeah, and when I was doing the derivatives of ln's before, I wouldn't put the 1 up there. I would just put the derivative of the inside on top. Which this time, the derivative of cosine is negative sine. If you didn't know the derivative of cosine or the derivative of sine, you just need to memorize them. It's not that you're missing some secret to the universe, you just haven't put in the work to memorize it. That's right, I'm calling you out. Yeah, you didn't do it. Those of you that did, good job. You did the work you were supposed to do. If you don't have them memorized already, just do some flashcards. It's no big deal. All right, so sorry about that. I just got distracted. Let's see. So, yeah, we would normally just write the derivative on top. Oh, yeah, so if you memorize them, great. If you didn't, come on. So derivative of cosine was negative sine, so I'll just put that on top, negative sine x. So I want to talk multiple choice. This would not be the answer on a multiple choice test. They would write what sine divided by cosine equals. So again, if you don't know what sine divided by cosine equals, just like off the top of your head, easily, without any help, without any like racking your brain, you probably want to spend a little bit of time doing a little bit of memorizing. And I feel really weird saying that because I love the idea that math shouldn't be about memorizing, but the AP exam is totally about memorizing. So it's just a definition. You just have to know that it's tangent. So it's negative tangent. Let's see, and then it says ln. All right, so 12 is ln, right? Y is equal to ln. Oh wait, no, I'm using cursive ln so that I'm not confusing. Ln of ln x. I'm saying ln and thinking of Ellen DeGeneres just for fun. Okay, so well, what's the most outside thing that we have? The natural log. What's the derivative of the natural log? 1 over the insides. I put the 1 on top again, jeez. Actually, I'm gonna write times this time because I'm kind of looking a little bit weird. So 1 over the insides. Well then, what's the inside? Natural log of x. What's the derivative of natural log of x? 1 over x. So this one actually was better not to put the 1 over x on top because that would look like this, 1 over x. And now we have this compound fraction that we have to deal with. So instead of doing that, this was a fortuitous mistake on my part. So 1 over x ln x. Cool. So something that, this is usually an AP question. So we see something like this. Y is equal to the natural log of x sine x. And at first glance, you're like, cool, I get to do product rule on the inside. You totally could if you want to. This would be 1 over x sine x times the derivative of the insides, which is going to be take the derivative of the first one, leave the second one alone, then take the derivative of the second one, leave the first one alone. And this would be totally true. And we could even probably do some cleaning up, put this on top, do some canceling, blah, blah, blah. You know, totally possible. However, don't do that. Instead, do this. Hey, what does times do inside a log? Changes it to plus. This is true. Y prime is equal to 1 over x plus 1 over sine of x times cosine of x. Right? Left it alone, multiplied by the derivative. Oh snap, we got 1 over x plus, now cosine over sine is cotangent. This is better than that, I guarantee you. Well, and they wouldn't show this as the answer, they would show this as the answer. So, and then 14, oh my gosh, 14's horrible to do without using log rules. With log rules, super easy. It says it's ln square root x squared plus 2x. So here I can drop the 1/2 out front. Oh, I'm sorry. I am in like autopilot mode. Let me back up. Okay, so let's rewrite this. Let's think about this. This is x squared plus 2x to the 1/2 power. So just remember that there's a log rule that says if there's an exponent on the inside, we can drop it out front just as a coefficient of the natural log. So I can say this is 1/2 times the natural log of x squared plus 2x. So I'm glad this is our second example of these because a plus inside a log does not convert to something else. The only things that we can take a log and break apart is if there's an exponent, we can bring it out front. If there's times inside, we can bring it into plus. And if there's divide inside, we can break it out into minus. I do see a little trick here that I could do though. So the first way, I would just go, okay, well it's 1/2 times, notice how I just extended it. This is gonna go on the bottom, right? 1 over this. And then its derivative is gonna go on top. So you got the x squared plus 2x on the bottom and then 2x plus 2 on the top. That's honestly, like, I don't think that the way I'm about to do it's any better, but it's fun, so I'm gonna do that. So I could think about this before I take the derivative. I could go, hey, this is 1/2 natural log of x times x plus 2, right? And factor it out. Now I have x times x plus 2, so I could say this is 1/2 natural log of x plus 1/2 natural log of x plus 2. And this derivative now is just 1 over 2x plus 1 over 2x plus 2. So this and this are equivalent statements, unless I made a silly mistake somewhere. So, yeah. Oh, sorry for the upside down stuff. I hope that's not too annoying. More upside down stuff. All right. Let's see. So, number 15, y is equal to the natural log of x squared over 3x minus 2. All right, well, 15, let's see, let's break this up first. So we can say this is natural log of x squared minus natural log of 3x minus 2. Already, this looks a lot nicer. And I can bring the 2 out front too and say this is 2 natural log of x minus natural log of 3x minus 2. So now when I take the derivative, I'll just get 2 over x minus 1 over 3x minus 2. This one is kind of a habit for me. Not a very good habit, because I'm maybe doing times 3, but instead of doing times 3 on the end, let's just do times 3 on the top. There, I never wrote the 1 to begin with. Cool. So then we get to 16. Natural log, big ol' square root, x squared minus 1 over x squared plus 1. So in this one, this is all to the 1/2 power. So I'm going to bring a 1/2 out front. some of you are going to want to do this in one step. Do it. I fully encourage it. I'm showing these steps. Honestly, it's a little painful writing every single step. Because I'm like, well, I see it's divide, so why don't I just break it up now too? But, so this 1/2 is going to be on both of them. You could also put the 1/2 out front and put parentheses around the whole thing. It's really pick your poison, whatever you're more comfortable with. And then you have to decide, do I want to break this up into x plus 1, x minus 1? I don't know if it's going to make a difference at this point. So, or like in terms of like ease of problem. So here we got 2 times x squared minus 1. On the top we'll have a 2x, because that's the derivative of the inside. Then here, we got a 1 over 2. We got our x squared plus 1, then times a 2x. I did the 1 again. Cool. So, yeah, it's the problems. That's what they are. Oh, cool. Then 17, he's like, hey, remember implicit derivatives? No, you're doing them anyway. Also, if you forget implicit derivatives, you have a very short-term memory. So let's talk about this. Let's do the hard part first and make sure to write the 0 over here when taking the derivative. You all know I messed that up a lot. So on the left-hand side, we'll get our 2x. Then this will be minus 3 over y. Right? That's 3 times the derivative of ln y. But it's very important for us to remember, oh yeah, I got to then multiply by dy dx, or y prime. Then plus 2y, that's the derivative of that, times dy dx. So now my goal is to get y prime by itself, or get my dy dx by itself. So if I do that, I'm going to subtract the 2x from both sides, and then we'll have 3 over y dy dx plus 2y dy dx is equal to negative 2x. Factor out the dy dx, and we will have negative 3 over y plus 2y. Now, you might see what I see, and you might go, uh-oh, I see fractions on fractions incoming, because we're about to divide by this. So now we got negative 2x over negative 3 over y plus 2y. And that's nasty, but remember, we can go through and multiply all of them by this common denominator. Cancel it out, and we'll get negative 2xy. This is why I haven't been using this marker. Negative 3 plus 2y squared. Ew. All right, so that's my dy dx. So, I want to skip number 18 because I'm getting annoyed of doing these examples. I'm not going to skip number 18. I'm going to do it. I'm going to go through and do it. 18 asks us for the equation of the tangent line. So good review for us. So here if I do, well, the equation of the tangent line, well, I already know at this point I can do y minus 4 is equal to something times x minus 1. I just got to find out what that number is. And we get that by finding the derivative, right? The slope of the tangent line is the derivative. And that's m right there. So y prime, this derivative isn't too bad. 4x squared turns into 8x. Then this one, dang, there's a minus in there, so I can't break it apart. So it's going to be minus the derivative of the natural log, which is 2x squared minus 1, times the derivative of the inside, which is going to be 4x on the top. Remember that 4x and 2x squared can't cancel. There's that minus 1 there. No canceling allowed there. Well, now I just plug in the 1 to find out what y prime is. It's going to be 8 minus 4 over 2 times 1 is 2. So 8 minus 4, so I get 4. 4. I'm done. So, cool. Onward and upward. Our next one says 19 y is equal to e to the 5x. Cool, so we're gonna, wait a minute. This doesn't say ln anymore. All right, back up. If y is equal to e to the x, I showed you guys this in class last time. Y prime is equal to e to the x. And I'll do a proof of it in a separate video. Okay, so here, y is equal to e to the 5x. Well, then the derivative of that, the biggest thing we see is e to the something. So the derivative of e to the something is just e to the something. Just make sure that you do chain rule after that. The derivative of 5x is 5, so I'm going to say it's 5 e to the 5x. You could have written e to the 5x times 5, but like that's more writing and it looks wonky. Just put the 5 out front. 20 says y equals 4 e to the 1 minus 2x. Oh man, it's going to be so hard and so complicated, and I'm going to cry, and it's so difficult. Some of you still question about, like, do I need to do product rule? But I want to remind you that a constant multiplied by a differentiable function does not change the derivative. The constant just sits there. You can do quotient rule on this. Remember that the derivative of 4 is 0. And so doing, did I say quotient rule? I meant to say product rule. Doing product rule here, there's going to be a 0 for one of them. It's going to kill that whole piece of it. So you don't need to do product rule, but it still works. Anyway, so here, the derivative of this is just this times the derivative of the inside. So 1 minus 2x. Let's see, that's just going to be negative 2. So personally, I wouldn't do that. Personally, what I would do is I'd be like, okay, well, I know it's going to be 1 minus 2x, and then it's going to be 4 times the negative 2, so negative 8. That's how I would do it. And 21, y is equal to e to the 1 over x. Okay, G, y prime is e to the 1 over x. Multiplied by the derivative of the inside. So I'm going to put that up front. Just want to remind you, 1 over x is the same as saying x to the negative 1. So the derivative of that is going to be negative x to the negative 2. Or we just rewrite this as negative 1 over x squared, e to the 1 over x. Or if you want to look even smoother, negative e to the 1 over x squared. But this is not allowed because of the negative exponent. So this is an illegal answer format. It's true, it's just not the right way to write it. This is fine, this is fine. All right, let's keep going. 20 dose. Y is equal to 2 e to the root x. So y prime is equal to 2 e to the root x times the derivative of the inside. which is 1 over 2 root x. I'm not showing this derivative. I showed it earlier in the video. You can go back and watch that if you feel so inclined, but we know the derivative of the square root of x. So this is a really, really gross way to write this. Instead, I would write this as the 2's cancel. E to root x over root x. So let's see, 23. Sorry. So my pause right now is I didn't realize that he does these derivatives right now. That's fine. So I'm going to tell you something. So the real derivative of e to the x is not actually e to the x. The real derivative of e to the x is e to the x ln e. That's the real derivative. So let's think about this real quick though. Ln e. Remember, that's saying our base to what power gets us e. Remember, our base with ln is e. So e to what power gets us e? Well, it's 1. So this actually just turns into e to the x. So the truth behind this, I know, I'm a truther, behind this is that the derivative of e to the x is e to the x ln e. So I'm telling you this because if y is equal to 2 to the x, this is how it works. Y prime is going to be 2 to the x ln 2. And this goes for any base. So, oh, I just did 23 by accident. Okay. So 24 then is going to be 24 equals, no, 24, y equals 5 to the 3x plus 1. So y prime then is going to be 5 to the 3x plus 1 ln 5 with the derivative of this up front. So it's going to be 3 times 5 to the 3x plus 1 times ln 5. 25 says what? Come on, paper. Come on. It says y equals 6 to the x squared minus plus 2x minus 1. So then y prime is going to be 6 to the x squared plus 2x minus 1 ln 6. Then with the derivative of this, I like to put the derivative of that out front. You could put it at the end. It's totally fine. This is just my personal preference. 2x plus 2. So that's all that's happening with these. The last one we're going to do in this video. All we got to do, y prime is 1/4 to the x times the natural log of 1/4. So this is a situation where they might actually give us a slightly different answer than this, because we could rewrite this as 1 to the x over 4 to the x times natural log of 1 minus the natural log of 4. That's 1 divided by 4. So I could technically do, and when there's multiplication or division inside and no pluses and minuses, we can distribute the exponent. So 1 to the x will always be 1. That's 4 to the x. Then here, natural log of 1, let's think about this. This is saying e to what power gets me 1, and whatever power that is, that's the answer to this. So e to the 0th power gets me 1, so this is just 0. And so this is times negative natural log of 4. And so they might wind up writing the final answer to this as negative natural log of 4 over 4 to the x. So this turns into this. True? True. They're both true. This is just a different format. So I hope this has been helpful. After this, all of these, the stuff on the next page, it's just saying, hey, we've learned all kinds of different things about derivatives. Well, let's just do it now. So that's for next class. So bye.